My name is Kevin Harms. I work in the performance team at ALCF. We're going to talk to you guys about I/O optimization. Before I start, I wanted to just acknowledge some of my colleagues who developed most of the slides and content. All right, so I'll start with a brief overview. So you guys probably got overview on Theta, but I just want to review how I/O works in that. So in this picture, we have like compute nodes here, these light blue circles. They're connected into this Aries high-speed interconnect. Somewhere in this interconnect is what I'll just call right now an I/O node. So any I/O requests are going to travel through this network, come to this I/O node, and then come onto a different network, in this case InfiniBand, and come to the Lustre storage system. So one of the things you need to understand is some operations are going to travel all the way here to be completed. So you want to be careful about the request sizes you're making. Now, for Lustre, we do have a full client running on here, and so some caching and things like that. So not every I/O request needs to travel all the way back to here, but many do. So that's the main takeaway from this slide. We'll cover the actual storage system a little bit more later. So the next thing I want to go over is terminology. So if I say client, I'm going to be talking about the compute node and the Lustre client running there. That's what I mean by client. The I/O forwarding node that I talked about, the I/O node, that is going to be, they're called LNet nodes. Those are Lustre network routers. So if I say LNet, I'm talking about these intermediate nodes that you send traffic through. Then we have the metadata server, MDS. So if I say MDS, I'm talking about metadata. And then MDS, the storage associated with the metadata server is called MDT. You don't need to know these in detail other than if I say one of these acronyms, you know I'm talking about metadata. So for the actual data, those are the objects storage server. So these are the servers which your client requests are going to come to. And then the data that they live on is called object storage target. So if I say OSS or OST, I'm talking about where you're putting data. That's kind of just the main takeaway. And then we'll see more of this, that your data, everyone's metadata is on the metadata server. You don't have much control about this. But your data is on these OSTs, and you do have some influence about how that works. So we'll visit that more later. All right, so what file systems can you access? So I'll start with this one here. Your home is on a GPFS volume or spectrum scale, if you know it by that name. So that's mounted at GPFS Mira Home. So this is also cross-mounted with Mira. So if you had an account on Mira, your data is going to be mixed. All right. This is also accessed through a similar method, but it's Crepe's data virtualization service. So they're also going through the I/O nodes, but they work slightly different. We do not have the GPFS client running on the compute node. So various operations are going to be punished more because they're going to have to go all the way back to the GPFS server or the client that's running on the service node. This is a petabyte additional storage system. It's not meant for bulk I/O, so please don't do your performance runs into this file system. That's not going to be ideal. It's for storing your code, storing your binaries. You can put input files here if you just need to read it from one rank or something. That's going to be okay. But the focus of this talk is going to be on this left-hand side, which is our project file system, which is Lustre. And that's mounted on Lustre Data FS0. It's at this soft link projects, and then your project name. We're running Lustre 2.7, so here's the key notes. We have 10 petabytes. We have 56 storage servers, and each storage server has one OST. So we have 56 OSTs. So remember that, 56 OSTs. And here's some nominal performance. Basically, the absolute peak best case performance you can get is 240 gigabytes a second for write or read, but these would be more. It's easier to achieve this read number. This write number is a bit harder, so 170 is a good target for hitting peak performance. And then a single OST is around 6 gigabytes per second. So if at some point you seem to be like, man, the best I can do is 6 gig a second, maybe you're just using one OST. The other thing, as I was saying in the previous slide, the Lustre client is running on the compute node, and it has cache. So you can get caching effects. So if you're writing small amounts of data, you could see like incredible performance because it's just written into the memory. It's not actually been flushed back to the file system yet. So you need to close the file or flush the data to get that to happen. So if you start seeing very high performance, that's fine. It's just coming out of the cache. All right, so now I'm going to talk a little bit about different I/O models you might use or you could use. So first is POSIX. Lustre is fully compliant. So this is a standard interface most of you are probably familiar with, and that's kind of the base level API you could use for the system. Moving up from there is MPIO. So if you're not familiar with MPIO, it was designed to support parallel I/O. It's a subsection of the MPI standard, so there's many I/O interfaces. And so there's two major modes. There's one called independent, and independent is mostly like POSIX, where you're doing read or write. Everything's independent from the rank you're executing your I/O on. You can still do more advanced things with file views and data types. Then there's collective I/O. And so collective allows you to basically, whatever communicator you define, all the ranks in that communicator are going to cooperate doing I/O. And this allows it to perform various optimizations. So I don't have a slide on what all those are, but the basic concept is various ranks are going to send their data to some other rank who will then aggregate that data together and then write it as one buffer. So basically the idea of collective I/O is to if you have a unfriendly I/O pattern, like lots of discontiguous regions that you're writing from the same rank, this will help improve the performance of that. So I definitely suggest checking out MPIO if you're not using it. The next layer up would be I/O library. So we definitely recommend using some I/O library unless you're really dedicated to writing your own I/O. So we have Crepe provides HDF5 in parallel mode. We also have NetCDF and then parallel NetCDF. So parallel NetCDF, all those interfaces are parallel. So whenever you're using that, you're doing parallel I/O. In HDF5, when you use all of the interfaces are similar or essentially the same, and so you determine how you're using it by setting properties. So in this case, for example, if you want to create properties for the data transfer, you can create a property list. Then you want to set, using this interface up here, data transfer parallel, MPIO, and then you can say, do I want independent I/O or do I want collective I/O? And there's, of course, many more properties that you can set. But so in HDF5, to get correct performance, you're going to need to go and set a few of these properties. So I suggest if you're just using base POSIX or you're starting at you're just running a cluster or something, and you're stepping up to this machine, investigate one of these MPIO libraries. They have some portability. Will make your life a lot easier. All right. The next thing is to talk about is files. So people tend to love files. You can use a lot of files if you want, but here's some recommendations from us on how you should manage your files. So our Lustre file system will scale well to on the order of 10,000 files. So if you put this in context, if you're going to run 4,000 nodes and 64 ranks per node, you're in the 200,000 file range. That you might start getting overhead from I/O on metadata. So you might want to revisit thinking about how you're going to do I/O in that case. But if you're running at like 256 nodes, you're maybe comfortably in this range. Doing a file per process is fine. Also, our system defaults will work well for a file per process. Now, if you want to use single shared file, you're going to want to change our default settings, so I'm going to go over that later. Scaling can be somewhat limited based on its lock contention. So if you ever have a case where the file system block size is 1 megabyte, if you're trying to write into a region that's shared by 2 different files, those become serialized because only one file can own the lock for that region. This is where you can get improvements from MPIO because MPIO is going to aggregate those into block-aligned writes, and that will mitigate some of the contention. So, and in general, I'm not advocating for a single shared file or file per process. Both of those will work okay on Lustre. You can also use a combination of those, often termed by subfiling, where maybe if you're running 4,000 nodes, you want to use 256 files, you're going to break those into communicators and create some kind of subfiling. Any of those approaches is fine. All right, so now I'm going to start talking a little bit about how you're going to do some optimization of whatever I/O code you might have. So the most important thing to learn from this presentation is this thing on Lustre striping. If you learn nothing else, learn this part. The slides might start getting more dense as I go. They'll eventually be available. You can use those as a reference. But, all right, so let's consider you have 8 megabytes. We can say file, but just think about I have 8 megabytes of data. In our default settings, we have the stripe size is 1 megabyte. That's like what Lustre is optimized for, so anywhere that's running Lustre is probably using 1 megabyte. That means you have 8 chunks of data. So when you write your file to the storage system, it's going to be in these 8 chunks. And because the default is stripe count 1, this is on 1 OST. So going back to what I said in the beginning, you're not going to get performance exceeding 6 gigabytes a second because you're only using 1 OST. So if you were to set the stripe count to 4, now you will be using 4 OSTs. So your data will get broken apart in 1 megabyte chunks. And so you see these light blue ones will still both be on OST 4, but now we're also using 3 additional OSTs. So in theory, our performance has gone up by a factor of 4. That would be ideal. You're not going to always see that, but that's the concept, right? And then additionally going to 8, now you have a OST that's your data is spread across 8 different OSTs. So this is where you'll get the parallelism from the file system. So, like I said, this topic is the most important thing. As long as you learn this, you're good. All right, so now how to do this in practice. So there's a parameter called stripe count. Our default is 1. That's good for certain things, bad for others. Our stripe size is 1 megabyte. That's kind of what Lustre is optimized for. But changing this to larger values might be useful. I'm not sure that there's any situation where making it smaller would ever be good. But larger, yes. Okay, there's also a parameter called stripe offset. We recommend you never set that. That's just choosing which of the OSTs you're going to start on. There's no reason to set that unless you're trying to do some I/O study or something. The system will choose the correct offset. Like I said, the stripe count can be a number between 1 and 56. So 57 is not going to be a legal setting. We have 56 OSTs. You can also use the value -1, which would be maximum. So if you want to write something that works on any Lustre system, you can put stripe count -1 if you always know, I just want the maximum OSTs. And then you set this, the parameters are set when the file is created. So if you want to restripe the file, you want to give different settings. For example, let's say you copied a file onto the system, and then you forgot to set the stripe parameters, but you want to read it from your job, and you want to get more parallelism. Then the only way to change these settings is to make a copy of the file and make sure that the settings are set correctly for your copy. All right. So what numbers would you use? So our default is kind of set up for the file per process case. You're going to use a stripe count of 1, but let's say you're using 1,000 files in parallel. So you're going to be using all 56 OSTs because every file is going to be assigned to a different OST. So that's going to maximize your parallelism. and default stripe of 1 is good. Now, if you're using a shared file, you're going to want it, and it's large. So I put greater than 1 gigabyte here. You can argue about exactly what size is good, but certainly when you're getting to a gigabyte, you're going to be distributing your file widely. So we're recommending using not necessarily a maximum. You can do that, but 48 will still get you the highest level performance. So you can go larger. Whether or not you'll actually get any more performance is another matter. In this case, you can also look at these larger stripe sizes, and so we suggested testing values between 8 and 32. Also to note, we didn't, so I said collectives. Collectives uses buffer. So on the node that's buffering, the collective buffer size you have set will determine what the stripe size is. So if MPIO creates your file for you, it will specifically set the collective buffer size to be equal to the stripe size. And then if you just have a small file, regardless, the default of 1 or maybe 2 is reasonable for small files. So these are your guidelines for setting the stripe size. So how do you do that? There's a command this is a command you would run from the shell, LFS set stripe. Okay? So ideally you're going to use it on a directory. So here's the example. The directory can be named anything. So this is where, let's say, I'm going to put my checkpoints. I'm going to make this directory. I'm going to then set the stripe to the count, and here's the size. Now, if you're like, I like 1 megabyte, you don't need to put -s. Just set this. So if you want to use the whole system, like I said, you could put -1 in here. You could also put 48. All right? So that's how you're going to do that. Then, as shown there, the next thing is get stripe. So if you want to check, like, wait, what is my stripe setting for this file? I'm not sure. You can use get stripe. Okay? And so I guess, sorry, I didn't mention this, but implicitly, the idea is files created in a directory inherit the directory settings. You could, like, for example, I'll show later with other mechanisms to set the settings. Those can override these. But for the, let's say you're just using POSIX, the simplest thing, you can just set this directory to the settings you want. Files will inherit those settings. So here's just an example. I'll just create 2 empty files. You can check their stripe settings. You'll see, okay, they have a stripe count of 4, and then they're 8 megabytes in size. There are other ways to do it. So for example, PNetCDF and HDF5 use MPIO under it. There's ways in MPIO to say, here's a hint, I want the files to be configured this way. They will use those settings. But if you're unsure, or you just want to be sure, you can create this directory and set them. If the file settings weren't given during the creation, they'll be inherited from this folder. But if there's any question, just run get stripe on the file. It'll tell you the settings. It gives you more details. Like, for instance, we sent stripe count of 4. So for here's it's allocated 8 megabyte chunks. Here's where they are. These are more details that you don't need. The main thing is the count and the size. Correct. So if you want to, the question was how you have a file and you want to change it. You can create a directory with your updated settings and then just create a copy of the file. All right. So other ways to set this. So the question is, can you do this in other libraries? So some particular, for example, HDF5 might have a HDF5 specific way, but since it uses MPIO, you can use this mpich MPIO hints. Now these are from Crepe MPIO. All right, so you can set the striping size with striping unit and then the striping factor to set the count. So then this environment variable will tell Crepe's MPIO how you want the file configured. All right. So going to the optimization for collective. So as I was saying before, the node which will be collecting, there'll be some number of nodes collecting the data from the other rings. So first there's a number of aggregators, and you set that by the CB nodes variable and then the CB nodes multiplier. So the larger number of aggregators you have, potentially the more parallelism you have, but also you have more people contending for your file. So more is not necessarily better. And there's a default setting with, I don't recall the exact, but I think it's 1 per node. So for example, if you're running 64 ranks per node, 1 rank will be the aggregator for that node. Then there's also the collective buffer size. So this is going to influence, like I said, the stripe size. So I believe the default currently for Romeo is 16 megabytes, but you could set this higher or you could set this lower. And there's a lot more information you can use, man, and intro MPI. MPIO is only 1 fraction of data in here. This small text here is some other ideas to think about. Again, you can reference that, but the core idea is that you have to sometimes experiment. Unfortunately, there isn't a single one-size-fits-all solution to all I/O. They are your compute nodes. So you have a rank running. So you have, let's say I'm running on 10 nodes, and each node has 10 ranks. So I have 100 ranks. Okay, the aggregate. So if let's say I have the total aggregators is 10, I will have 1 aggregator on each node, and it will aggregate the obviously there's some settings that'll do some topology aware. So the nodes that are sharing, the ranks that are sharing the same node will collect onto that. Or if you distributed your processes in some different way, like this process 1 and 10 are on different nodes, like they're not sequentially, you might get some data transfer to get the ordering correct. Well, when you call, so I'm going to attempt to go backwards here. Yeah. Where did I have it? So when you call this function, MPI, let's say write all. Right during, this is a synchronous call. So all I/O is going to happen while this is. But what happens in this call is not just sending data to the file system. My rank might transmit data to another rank. That rank will receive those data, then pack those into 1 large buffer and write it when it knows it has all contributions from the other ranks it should. The idea behind this is that, one, if you have some discontiguous pattern, so if you're trying to write something where I'm trying to write into, like, let's say 1 megabyte block here and then another megabyte block over here, I don't want to write those from the same rank. So some of it will go to 1 rank, some of it to another. And this will all get distributed, and then when the aggregator that writes, it's going to have 1 contiguous block written to the file system. Now the downside of collective I/O is that on the shared file, you're having this contention for locks because Lustre has strong POSIX consistency, so only 1 person can lock 1 block at a time. And so if you have many blocks being written from many nodes, it takes a while for the lock manager to sort all that out. All right, so now to just give you some ideas of performance. In this case, we're using 256 nodes with 16 ranks per node, and then each one is writing 8 megabytes. All right, so we're using independent I/O. So that means there's no collective operations. Everyone's writing independently. In this case, he also has the client-side caching disabled. And you can see the effect of using how many OSTs. So if this first part is, I believe, the number of, this is the file, the size, I believe. So how many times are you writing this, I think? So you can see for 1 OST that this workload is capped by the performance of 1 OST. And so as you increase, you see that you're going to get more performance. Yeah, this is the stripe size. So we can see if you go up to the maximum, you can get a little bit more performance, but you're not going to get significantly more performance. So that's why we kind of suggest using 48. And so you can see read performance is quite a bit higher than write performance, and this has to do with, again, file locking overhead. All right, so here is a similar graph. You'll notice, I'll just go back for a second. So look at the Y range. So you'll see that here our top is 140 gigabytes per second. Here it's 90. So again, you'll see the same effect. Increasing number of OSTs increases performance. The larger stripe sizes are doing better at these larger sizes. But you can see our write performance isn't quite as good, you know. Crepe's been working on this, so I believe on the current system it should be slightly better than these graphs. But yes, this one, why these are slightly different, I know. He has caching enabled here versus not, and then 1 megabyte. But because it's collective, the 1 megabyte is irrelevant. It's a collective buffer size. It's going to be influencing what's written to the file system, and that's decided by this. So if our collective buffer size is 16, we're writing 16 megabyte chunks. I know this is a little bit odd, but so we're doing collectives. Each rank is going to send 1 megabyte, but not all ranks will send that 1 megabyte to the storage system directly. 15 of them, let's say, will send it to a node. The 15th rank will take its 1 megabyte, add it to the 15, and then write it in this one collective chunk. So when you have collective, you have communication and I/O both together in one I/O call. But this will allow you to get better performance on a shared file to some level. But in this case, everything's contiguous, like these are writing 1 megabyte contiguous. And this is also contiguous. So you see independent write is significantly better because the overhead on this that's happening is too large. So it's not as good as write. But if you're using discontiguous data, you'll probably see a benefit from collective versus independent. It really depends on your I/O profile. And so what I mean by discontiguous is if you're writing something and I want to write it to multiple different offsets, that's what I mean by discontiguous. But if you're writing one large buffer and it goes all contiguously written to the same interface, then I would start with independent. All right. So now we're going to move on to profiling. So now if you're not satisfied with your I/O performance, I would, one, definitely check it. So you should put some timing in your code and look at how long I/O is taking. You know, our target is like 5% of your runtime. So if you're in like 20%, we should probably work on your I/O and try to improve it. Unless for some reason data processing is your core thing you're doing. So one of the tools we have installed is called Darshan. And this is statistical profiling. So it can't give exact answers. It can just give us ideas about what's going on. We have this turned on by default. So if you use the Crepe wrappers and you're using MPI, you'll have Darshan included. And if your job terminates successfully, it will write a log. And so this log can be found at this location. Logs Theta FS0 logs Darshan Theta, then year, month, day. And then you can look for your username. And that day, the day is chosen by, I believe, the start time of your job. So if your job runs over a day, you might have to look in 2 different days. All right, so when you have this log, it's a binary thing, so you need to process it. So we have 2 tools. DarshanJobSummary.pl will create a PDF with various graphs in it. In order to use this, you also have to load this module first, Tech Live. So load that, you can run this, and then it'll produce a PDF, and I'll show you what's in there. The other one we have is this called Darshan Parser, and it's a prints text to the command line. This is useful when you know exactly what you're looking for. You can look in here. To understand what's output, you're going to need to read the Darshan documentation because basically each line is one counter for one file. So you have to go look and see what counters of interest you have. But here's what the PDF generation. So I think it's 3 pages long. This is just half of 1 page. So you'll get graphs such as this, which just shows you where are you spending time. So this is like IORs of IO benchmarks. All the time is in writing the I/O. So yours should not look like this. You should have this pink bar, and then your I/O should be down here as 5 or 10%. You also have graphs for how many operations are you doing, what types are they. We have graphs for like histograms of the size of operations, common access sizes. You'll see at the top also, as I said before, this is statistical, so we can't tell anything exact. So it's giving you a performance estimate. This is based on taking the counters we find and applying some heuristic. If you're violating our heuristic, then this estimate could be grossly wrong, which is fine. That's why I'm saying you should check the performance of your I/O yourself, but you can see if the performance here is similar to the performance that you think you're getting, and if they're different, we can look at that. But if you send mail to support and you're asking me to help you diagnose your I/O and improve it, like this is the first thing I want to see. All right. Next, you can use some, Crepe provides some environment variables that you can set that will then print some things out. So these are going to have slightly higher overhead. Now, the overhead to collecting this data versus the call to I/O is generally large enough that these, you may not see these, but these are going to give you details about your access patterns and data written on a per file basis. I'll point to this one if you use collective I/O. Setting the timers here, you can kind of see how much time are you spending in the communication aspect versus the I/O aspect. So these things can be interesting. All right, and the last tool I'm going to point out is Crepe. So I believe you got a presentation for Crepe already, but one of the things it can do is also I/O, among the other things. It's a binary instrumenter, so once you've built your binary, you can call pat build, say you want to look at I/O, and let's say MPI. It'll instrument your binary. You run your application. There's going to be some overhead to doing this. You're going to run it, and then it's going to write out some directory. You use the pat report to analyze it. It's going to spit out a bunch of things. Some of those tables will be tables on I/O. So this one's for reading, so you can see, okay, how much time was spent reading, how much data was read. Just simple calculation between these two will give you the rate. You can see how much you're writing in each individual call, so forth. So again, it will give you a good baseline for looking at what your I/O does. All right. So that's kind of my main topics on the parallel file system. I have one last section that's on something different, so I'll ask if there's any additional questions on parallel I/O or Luster. Python. Okay, so you can, so obviously if you're doing file per process and each of your files is writing from a Python process, as I said, you can have the default one OST. You're going to get good performance. You'll be using all OSTs, assuming you're writing hundreds or thousands of files. So if you want to do a shared file in Python, I don't know if MPI for Pi exposes the MPIO interfaces. I don't think so. So from that perspective, you would have to kind of do you'll have to be careful that you're not writing over. You don't want to share blocks between different ranks, so you want to be careful about that. Otherwise, you'll get into a lot of overhead from locking. But I believe you can use HDF5 from Python. So there is a Pi for HDF5. I don't remember the exact module name. But that will let you do HDF5, and you can set all the standard HDF5 parameters that you would in C. All right, so I'll move on to my last part, which is something different. So Theta has these SSDs around every compute node. And so if you look at, this is the approximate performance of a single SSD. You get a gigabyte read and maybe half a gigabyte write. Obviously, this performance is far inferior to the parallel file system. However, if you're going to run on a large number of these compute nodes, the aggregate performance can start to exceed that of the file system. So that's where these things become interesting. The downside is your operations are contained to what's on a single node. So if you want one node to read the data from another node, you're going to have to do that yourself by some means. We don't have any kind of software stack for that. There are existing software stacks that you can investigate for that, but we don't have any installed. The simplest use cases you can do is if you have something that uses intermediate files or you have like an out-of-core solution, you can put that on the SSD, and that's going to speed up things a lot. You can also use it if you have a bunch of small files that you need to work on either during the run, and then you're going to aggregate them and write something out at the end of the run. Again, you could store these here during the run. You can also, in this case, like let's say I have initialization after read many files. I can put them in one tar, and then before my job starts, copy that tar file to every place and then untar it. And then I can just read those small files normally, but with no penalty. The other main thing to know is if you want to use these SSDs, you have to get permission. And here's what you do. But basically, you send an email to support. You say why you want to use the SSD, what's your use case. That's mainly to prevent you from just abusing the SSD. All right, so how do you use it if you have access? You're going to, in your Q sub, you have to add this -- adders SSD required. That will make sure that you can write to the SSDs when your job starts. This parameter here, SSD size equals 128, is optional. Right now, every compute node has the exact same SSD size, so there's no issue, and every node has an SSD. But if at some point in the future, if nodes had different size SSDs or some nodes didn't have SSDs, you're going to want to set this. Now, so what do you do once you submitted your job, you're running? There's a directory, local scratch. You can create files in here. So just, create local scratch, /something. You can make directories, whatever hierarchy you want to do in here. When your job terminates, this data is gone. It's all deleted. So you can't run a job and then run another job later and get this data back. It's only during the lifetime of the job. And as I said, the reason why you would use this is you can get aggregate performance far exceeding that of the file system once you get the node count to be high enough. So if we just look at this left-hand graph, the dashed lines are from the, read is the dashed line. So you see SSD is significantly exceeding that of Lustre, and then on the right side as well, you can get over Lustre performance when you're using 1K nodes. All right, so in summary, use the Lustre file system. That's the main thing. Setting the stripe count and set size according to your usage. If you can do these two, you're doing well. Investigate I/O libraries or MPIO if you don't already have some kind of I/O model. And then if you do check your I/O performance and it does appear to be not achieving what you think, check these things. But if you're like, I think I have the stripe count and stripe size set well, then let's use Darshan or some of these other tools to investigate. And as always, if you do need help, you can send an email to support, and staff's always available. Any questions on the SSD or I/O overall? If you have a link from your home file system to the Lustre file system, that's fine. You can access it through that link. But no, it'll be fine. It'll be whatever the entire project file system is just symlinks anyways. So when you write the /project something, that's just a symlink that's linking into the Lustre project file. So yes, symlinks won't degrade anything. The only thing where symlinks can trip up things is, like in Darshan, it will collect some data about Lustre, but only if it knows your file's on Lustre. And if you have a symlink, it might be like, oh, your file's on GPFS. And your performance won't be impacted, but some profiling tools might get tripped up because they think your file is on a different file system because they don't fully resolve the path because that's expensive. So typically most profiling tools don't do that. That's the only thing where symlinks can get tricky.